Statistics is the study of data, and taking that data, organizing it, and figuring out what the data is telling us is data analysis. In statistics, we are going to be discussing or focusing on the who we are studying and what we are studying. The data will be coming from some group of individuals, and that's who is being measured. And the variables are what is being measured. So the who is being measured is the individual, and the what that is being measured is the variable. Now keep in mind that the individual does not necessarily have to be a person or people. Okay, so the individuals do not have to be people. They can be anything that we are measuring. These variables are going to fall into two different types that we're going to be talking about: categorical and quantitative. Categorical places the individuals into several groups, so into categories or groups. And the quantitative takes numerical values to that we might want to find the average on. Okay, so let's take test scores, your test grades. If we're talking about the letter grades, that is categorical. So the letter grades would be categorical, which would be like getting an A or a B or a pass grade, where quantitative would be the scores that you made on the test, such as a 90 or a 95 or a 100, things that we might want to find the average of. Normally we think of quantitative as number values, but sometimes number values can be categorical, such as your zip codes or area codes. We're not going to try to get an average of your zip codes or an average of your area codes. Some data could go either way, such as your age. We could take your ages in this classroom and find the average of them, and that way it would be quantitative. But if I were putting you into a category of students 15 to 18, now it's categorical. So there is some data that can go either way. Quantitative variables may have values that are really close together, or they may be spread apart. This pattern of variability is called the distribution. So what is distribution? Distribution of a variable tells us what values the variable takes and how often it takes these values. So it tells us what values the variable takes and how often it takes these values. It would now be a good time to stop this and check your understanding. Be right back. So who were the individuals that were in Jake's studies? The cars in the student parking lot. What values did Jake measure and identify each as categorical or quantitative? He measured the car's model, which was categorical, the year, quantitative, color, categorical, number of cylinders, quantitative, gas mileage, quantitative, whether it has a navigational system, categorical, and the weight, which is quantitative. The distribution of categorical variables lists the categories by either the count or percent of the individuals who fall into each of these categories. Let's say you polled 80 people and asked them their eye color and found that 45 people had blue eyes, 20 brown eyes, and 15 green eyes. This would be, if I wrote that as a table, that would be a frequency table. Now, if I changed those values to percents, where 56.25% had blue eyes, 25% had brown, and 18.75 had green eyes, this would now be a relative frequency table. So a frequency table is by the counts, a relative frequency table. We can then take the data that we have and put it into either a pie chart or a bar graph. Pie charts are used basically when you're comparing a part to a whole, such as the percent of A's in this class. We would be comparing part to the whole. So what is the most important aspect of pie charts and bar graphs? It's labeling. Label your axis. Label everything. If you don't label, it doesn't make any sense. Nobody will know what that bar graph means. So make sure that you label all your pie charts and bar graphs. I have another AP tip for you. Make sure that you label all your graphs. You can do a beautiful job on your graphs and still get marked off points if you do not label your graphs. So both pie charts and bar graphs show the distribution of categorical data. Use the pie charts only if you want to compare parts of a whole. A bar graph can compare any set of quantities that are measured in the same units. When is it inappropriate to use pie charts? When not analyzing parts of a whole. Although graphs are wonderful to look at and they tell us a lot of information, there are ways to make graphs misleading. One common way to make graphs misleading is the area principle. When we look at bar graphs, our eyes react to the area of the bars as well as the height. When the bars are the same width, the area will vary proportionately, and we get the correct picture. If they do not, it can be misleading. Another common way to make graphs misleading is by not beginning the y-axis at 0. This can mislead by making the data look like it's a lot smaller than it actually is. If we had a graph that started at $250 billion and was going down by $2,000 each year, if we started that graph at 200 billion instead of at 0, it would look like that graph was going down by a lot every year. But this would be very misleading because $2,000 a year when you're talking about $250 billion is not really very much. So the common ways are area principle and not beginning your y-axis at 0. So what's wrong with this graph? Well, as you can see, the areas are way distorted. The widths, remember that our width should always be the same with the part, the same width. We also need to look at this. This is 56 channels, which is more than half of this, but looking at the areas and comparing them, this looks a lot less than half of this area. And so this is very distorted. And this is some examples of misleading graphs. Not all of these are misleading. And your homework is there.